All right, we continue on here with estimation of contrasts of two or more treatment means. And so consider the linear combination of treatment means given by the sum, j going from 1 to t. I'm not showing the subs or the indices of summation here just to kind of keep things a little bit less cluttered on the screen, but the sum a sub j times mu sub j, where the a's are these coefficients that we're multiplying against the treatment means that define the linear combination. And we're looking specifically at situations where the sum of those coefficients, the sum of the a sub j's, is equal to 0. And what that implies is that the linear combination that we're looking at is a contrast, and it's a contrast of two or more of the treatment means. And so we know that in this kind of a situation, at least two of these things have to be non-zero in order to add. So if at least one of them is non-zero, then because they sum to 0, at least two have to be non-zero. And so we're looking at a contrast, which is another way of talking about a comparison, right? A contrast or a comparison among two or more of the treatment means. Now, an unbiased estimator of this contrast of treatment means is given by the same contrast, but of the point estimates of those treatment means. So again, we'll denote the estimate of our contrast by the sum a sub j times mu sub j with a big hat on top, right? So we're estimating that entire thing. And this is given by, because of linearity, all right, the sum, the same linear combination or contrast of the point estimates of the treatment means. So the sum of the a sub j's times the corresponding mu hat sub j's. So that's how we come up with a point estimate for this contrast that we've got here. Now, it can be shown that the variance of that point estimator is given by this expression. So the variance of the estimator of the sum a sub j times mu sub j, j going from 1 to t, is equal to 1 over r, 1 over the number of replications, 1 over the number of blocks, times the sum of the squared a sub j's, and then we multiply that by sigma squared, which is the variance of the model error term. Now, once we have that expression for the variance, we can take the square root of that to get the actual formula for the standard deviation of this point estimator, which is just the square root of that expression. Now, as was the case when we were looking at differences between treatment means and estimating those differences, notice that these expressions for the variance and the standard deviation of the contrast, or the estimated contrast, do not involve the block variance sigma beta squared, but only the error variance sigma squared. All right, and again, this is the reason this is the case is well, because it's a contrast, and what we're doing here, it's a comparison among two or more treatment means, and what happens is, again, mathematically, and this is kind of perhaps a little bit hidden in the mathematics, but what happens is we actually make those comparisons within each block, and when we do that, the variability due to the block cancels out or gets subtracted out, and then we take those estimates from each block and we average them. All right, and so the end result is that the variability associated with our estimator does not depend on the block-to-block variability. It does not depend on sigma squared sub beta, but it only depends on the the variability of the model error term, sigma squared. Again, since the error variance, sigma squared, is unknown, the actual variance and the actual standard deviation of our point estimator of the contrast cannot be calculated and therefore must be estimated. And again, we have estimators or we have an estimator of sigma squared. That's the mean squared error from the analysis of variance table. And so we can then come up with an estimator for the variance of this point estimator as well as the estimated standard deviation of that point estimator. And we get those by replacing sigma squared, the unknown sigma squared, by its estimate, the mean squared error. All right, now again, in this case, the distribution that we get the interval coefficient from is known. It's the t distribution with degrees of freedom equal to the degrees of freedom associated with the mean squared error, which again is r minus 1 times t minus 1. And so if what we want is a 1 minus alpha times 100% lower confidence limit for our contrast, then we start off with our point estimate and then go a distance to the left equal to the margin of error for the interval. All right, so and again, the margin of error is the product of the interval coefficient and the estimated standard deviation of the point estimator. All right, and so this would be the upper alpha percentage point of the t distribution with degrees of freedom equal to r minus 1 times t minus 1. All right, and then if we plug in the value for the estimated standard deviation of our point estimator, which again, let me go back one slide, is given by this expression, then we have the formula as we've expressed it here. So that is how we would calculate a lower confidence limit alone for the contrast of interest. Now, if what we wanted was an upper confidence limit, then again, all we would do is add that margin of error instead of subtracting it. All right, and so that's the only difference between the last slide and this slide. Again, notice that in both of those situations, for a lower confidence limit alone or an upper confidence limit alone, we don't divide alpha by 2. Okay? Now, if we want a two-sided confidence interval estimate of the contrast, then we are going to calculate the margin of error. We start off with our point estimator. We then calculate the margin of error, and then we go a distance to the left and to the right of our point estimator. In other words, we subtract and add the margin of error to and from the point estimate, and that gives us the lower and upper confidence limits for the confidence interval. And again, notice that because this is a two-sided confidence interval, we have to divide that alpha by 2. All right, and so the interval coefficient here is the upper alpha over 2 percentage point of the t distribution with degrees of freedom equal to r minus 1 times t minus 1.